first, just a couple words on logistics. So we're going to have lectures in here for the next 3 weeks. In weeks 2 and 3, we'll have some guest lectures by Professor Louise Lehner and Huan Yang. So that way you guys get to also be exposed to some of the other researchers at PI who also work in this field of strong gravity. So, of course, during the lectures, feel free to ask questions, point out when I make a mistake on the board, or so on. Hopefully it's a small class, so we're going to be pretty interactive. And even though it's first thing in the morning, everyone could get a big cup of coffee and then come ready to be engaged. So, in addition to the lectures, there's going to be a tutorial. Those will be Tuesday at 2 p.m. So hopefully we'll have the sort of instructions for the tutorial posted on the wiki beforehand, so you can take a look at those and come prepared. So the tutorials are going to involve some sort of low-key numerical work at the level of solving coupled ordinary differential equations and plotting. So for those, you're welcome to use whatever your favorite program is for integrating ODEs, whether it's Mathematica, NumPy or SciPy, Maple, MATLAB. So hopefully everyone is familiar with at least one of those and can come with that installed on their laptop. Just to get a feeling what people prefer to use, whose favorite method for integrating ODEs is Mathematica. If you just raise your hand. Okay, what about Python? Something else, MATLAB. Okay, so if you aren't familiar with any of those types of programs, maybe talk to Pablo or Gazelle beforehand. So, So by the way, the Sci Fellow is Gazel in the back, and our TA will be Pablo Bosch. So if you have any issues with attending the tutorials, be sure to talk to them beforehand. In addition to that, there'll be 3 problem sets. So those will be posted on Wednesday and then due the following Wednesday. So one thing I want to emphasize in this course is that, with the recent detections by LIGO of gravitational waves from merging black holes and neutron stars, we've really entered this new era where we're actually observing the dynamics of space-time. And so in this course, we'll try to develop some of the sort of theoretical tools and concepts that will allow us to understand the dynamics of space-time and can be used to explore a variety of settings, from simulating what happens when 2 binary black holes merge to exploring ADS-CFT in the nonlinear regime. So in this course, we're going to start out a little bit slowly in the first week, mainly looking at dynamics that happens on the fixed spacetime of a spinning black hole, or in cases where the black hole spacetime is very slowly changing, as for example when you're tapping into the black hole's rotational energy. Then in week 2, we're going to talk about how to formulate Einstein's equations as a set of dynamical equations that allow you to start with some initial conditions and then evolve forward in time to see what happens later. And as well as how to define things like what do we mean by a black hole horizon in a very dynamical setting. And then in week 3, we'll focus on gravitational waves, including things like how our gravitational waves are generated by things like 2 compact objects orbiting each other or a perturbed black hole, and a little bit about how gravitational waves are detected. So just to begin with, let's have a brief review and fix some conventions. So I'm going to assume everyone here has had at least an introductory GR course. So let's just review the basics. So first of all, in this course, we'll be using geometric units. That is Newton's constant g, the speed of light are both set to 1, since we're all advanced relativists now. For index conventions, be using A, B, C, and so on, the first letters of the alphabet to indicate for index, that's the space-time indices. And then I, j, k, and so on represent a 3 index. It's just a spatial index. So for example, we have a 4 vector. This would be the time component. And these would be the 3 spatial components. For metric signature, we'll use the so-called East Coast metric signature. Also known as the mostly plus. And that's not just because we're on the East Coast, because that's the right metric signature that everyone should use. So sort of the fundamental object in GR is the metric, which we'll denote as GAB. And from that, you can calculate proper distances on our four manifold. And we can use this metric to define the so-called Christoffel symbols. Which are the connection coefficients. And as we all remember, these are symmetric in these two indices here. As you can see, if you flip them, these two just flip, and then this one remains the same. And then once we have these Christoffel symbols, we can use them to define a covariant derivative on our manifold. So the way that's defined, if we act on sort of an arbitrary tensor with both upper and lower indices, we get a partial derivative. And then we have to contract with the Christoffel symbol for all these indices. We get a plus sign for the upper indices. And then more terms for all the upper indices, and then we get a minus sign for the lower indices. And then so on for all the lower indices. Yeah.
Just notation. The definition of the Christoffel wouldn't be maybe GCD, or just looking at the indices, and maybe some.
Sorry, where?
So the first G.
Oh, yep.
Yeah.
Yep. Thank you.
In the two.
On the C's downstairs should be these on the first two.
Oh yes. That.
That one's good.
Yep. There we go. Thank you. Yep. Any other mistakes? Okay. Yep. And so once we define this covariant derivative, then our metric is compatible with it. It just means the derivative with the covariant derivative of the metric is 0. Yeah, and so we can measure the curvature on a manifold with the Riemann tensor, which we can define by looking at the commutation relation acting on a vector, arbitrary vector. Yeah, so this object here is the Riemann tensor, and it tells us how basically the relation when you switch the covariant derivatives, which doesn't in general commute. And once we have this Riemann tensor, we can define a couple other objects just by contracting it. That includes the Ricci tensor, and then we contract it again to get the Ricci scalar. And finally, we're ready to define the Einstein tensor. And so, of course, the Einstein tensor lets us write down the Einstein equations in very compact form. And so here, TAB is the so-called stress energy tensor. So it encodes basically all the matter degrees of freedom, the energy density and the stress energy and the momentum density and so on. So for example, for a perfect fluid, our stress energy tensor looks like this. Where here rho is the energy density as seen by observer with velocity u, where u is the forward velocity of our fluid, and then p is the pressure. And then, of course, the stress energy must be conserved. But more than that, we usually want to impose some extra conditions on sort of what we consider to be reasonable types of matter, so-called energy conditions. I mean, we can note that if we don't impose any conditions on the types of matter that we have in our system, then we can really get any geometry we want, right? We could just write down an arbitrary metric, go through this calculation, calculate that arbitrary metric's Einstein tensor, and then just say, okay, let's have some matter that equals exactly that divided by 8 pi. So most of the time, to sort of, and if we do that, we're not necessarily doing physics. So usually we want to impose some sort of energy conditions on the stress energy tensor. So there's a number of different ones, but one we'll use commonly in this class is the so-called null energy condition. And what that states is that if you take the stress energy tensor and contract it with k, where k is a future-pointing null vector, an arbitrary one, then this quantity is greater than or equal to 0. So we can note, for example, for this perfect fluid case, that just gives us that this quantity is greater than or equal to 0. Because for a null vector, if we contract with the metric, we just get 0. So in particular, that means the pressure plus the energy density should be positive or positive or 0. So this is a somewhat mild energy restriction compared to some of the other ones. Okay, so that's basically a whirlwind review of the basics of general relativity. So any questions about that before we go on? Okay, so in this week, I want to mainly focus on the Kerr solution, which describes an isolated rotating black hole, and as well as some of the dynamics that happen on the background of Kerr spacetimes. So first, you might ask, what's so special about the Kerr solution, and why do we want to spend a whole week studying things that happen in Kerr solutions? So to answer that, let me first read you this very nice quote from Chandrasekhar, who's one of the pioneers of relativity. And the quote goes, "In my entire scientific life, extending over 45 years, the most shattering experience has been the realization that an exact solution of Einstein's equations of general relativity, discovered by the New Zealand mathematician Roy Kerr, provides the absolute exact representation of untold numbers of massive black holes that populate the universe." So what exactly did Chandrasekhar mean by that? So it turns out the Kerr solution is pretty special. So first of all, the Kerr solutions are actually the only possible stationary vacuum black hole solutions. So this statement is actually due to a series of work sort of in the late 60s and 70s by people like Israel, Carter, Robinson, and Hawking. They basically established that if you impose these conditions that your spacetime is stationary, you have no energy, then the Kerr solution is basically the only vacuum solution you can get representing a black hole. Another property of Kerr black holes is that if you make perturbations to them, they actually decay rapidly. So we'll discuss more of this in week 3 when we look at perturbations of black holes and their behavior. But sort of in that week, we'll sort of discuss how sort of generic perturbations of Kerr black holes actually decay exponentially. And so you quickly again approach the Kerr state. And what this means is that if you have generic gravitational collapse, then you expect the final state to just be a Kerr black hole, perhaps with some gravitational waves that radiate away to infinity. And that means we can just parameterize our solution by 2 quantities, the mass of the black hole and its angular momentum, as well as like the gravitational waves that get radiated to infinity. So this is the so-called no-hair property of black holes. You just need these couple of parameters to characterize them. And so here, of course, I'm ignoring matter charges, for example, the electromagnetic charge, which in most astrophysical settings aren't thought to be very significant. So any questions so far? There we go. All right, so let's write down the metric for the Kerr solution. So we have to choose particular coordinates. So here we'll work with Boyer-Lindquist coordinates to start with, which are a particularly convenient set. So that's the line element for Kerr. And then a couple of quantities we need to define here. So the sigma is just shorthand for this quantity, r squared plus a squared cosine squared theta. And this delta quantity is just shorthand for r squared plus a squared minus 2m times r. And so here, m is, of course, the mass of the black hole. This quantity a is the angular momentum of our spinning black hole divided by its mass. So in geometric units, this also has the same units as mass. And then a lot of times it'll be useful to refer to the dimensionless spin of the black hole, and that's just the angular momentum divided by the mass of the black hole squared. And so then this is a dimensionless unit, or a dimensionless number. And so, yeah, so you should be aware that conventions on this vary. So sometimes people use chi to be the dimensionless spin of the black hole, or sometimes they just use A to be the dimensionless spin of the black hole. I think that'll happen in the homework a couple times, so just be aware of the differences in notation. Okay, so let's consider this metric in a couple different limits. First, we can note that if we set a equal to 0, then we actually just recover the usual Schwarzschild metric, which I'm sure everyone here is familiar with. with just a black hole of mass m. And you'll notice that in particular, this term here will go away. And so the metric will just be diagonal. So let's consider the Kerr metric and another limit where we fix the dimensionless spin, and then let the mass of the black hole go to 0. So in that limit, the metric takes this form. So if we stare at that a little bit, we can realize that this is actually just Minkowski space, or flat space, in a particular set of coordinates. So we can go back to the usual Cartesian coordinates with the following coordinate transformation. So you can note here that these are actually so-called ellipsoidal coordinates. So phi is just the usual azimuthal coordinate. Theta is the so-called polar coordinate. And then in these coordinates, r equals 0 actually gets mapped to this ring of radius a. So the Kerr metric has a number of different symmetries. So let's talk about those.
If you take the m equal to 0 limit, do you have to accordingly take j to 0 limit? Does the a blow up in the coordinate transform?
Yeah, sorry, fix a, yeah.
J also.
Yeah, so yeah, basically J would be m times a, and we'll fix a and let m go to 0.
I have a question. When you said it's the only solution, stationary vacuum and black hole. So the proof for, I think there's a proof, and then for black hole, what does it mean? Does it mean there is a boundary condition they put in, or does it mean that in this limit it ends to be a Schwarzschild?
So, sorry, say again?
So when you said it's the only possible solution, which is a stationary vacuum and black hole.
Yeah, well, we could also get like a a flat space or something like that. But yeah, it's basically.
So stationary and vacuum is clear, but the black hole, is that, do they mean like singularity in the center and Minkowski asymptote? Is that, what does that definition mean?
Yeah, so though, I mean, I guess you could have some naked singularities. We'll talk in a second about how we can get if we take particular values of A here, we could actually get a naked singularity. But basically this is the only solution, modulo these, weird naked singularities, as long as we, don't want to just have flat space or something like that. Yeah.
Last simple question. You include also Schwarzschild in a limit A going to 0. Also Schwarzschild has the same properties, or?
Yeah. So Schwarzschild is just a special case of this with A equals 0. Yeah. Anything else? Yeah. So symmetries of Kerr. So the Kerr metric actually has two killing vectors. So first, let's remind ourselves what a killing vector is. So we say that a vector k is killing if it satisfies the following equation, that the Lie derivative with respect to k acting on the metric is 0. So to remind ourselves, the Lie derivative looks like this. That's just writing out the Lie derivative. And you can also write this equation where we replace these partial derivatives by their covariant derivatives. And that's just because the extra Christoffel terms will actually cancel out due to the symmetries of this equation. So it's equivalent to and if we specialize to the particular case of this tensor being the metric, then we can notice that the covariant derivative of the metric will vanish. So this first term will be 0. And then we're basically just left with these two terms. Which we can write compactly as this, where these parentheses just mean the symmetrization operation. So, and then divided by the number of the factorial, the number of indices. So we can note that our Kerr metric here, all the coefficients are independent of both the time coordinate t and the azimuthal coordinate phi. So looking at this expression here, we can immediately deduce that we have two coordinate vectors pointing in the phi and the time direction. Okay, so killing vectors of Kerr. So I'll use phi with a hat to denote the axisymmetric killing vector. And then T with a hat to denote the vector. This is just given by partial T. And having a time-like killing vector is what we mean when we say the solution is stationary. So, as a side note, Kerr is not a static metric, even though it's a stationary metric, unless this A parameter is equal to 0. That is, it has no angular momentum. And we can notice that just by considering letting t go to negative t. So in that instance, this dt d phi term will actually switch sign. And so we won't recover the same metric. So it's that term that basically spoils the metric being static. And so if you're like me, maybe you have a hard time remembering this difference between stationary and static. Basically, stationary is something that's continuously spinning, but not changing how it's spinning. So, for example, if you go to the PI gym, they have a stationary bike. So you're not going anywhere, but you're spinning the whole time. But if you had a static exercise bike, you wouldn't really be burning any calories. So that wouldn't be that useful. So it also turns out that Kerr, in addition to having these two killing vectors, actually also has a killing tensor. And so what do we mean by a killing tensor? That's a tensor that satisfies this equation. Which you can see is basically just a generalization of this equation, adding one more index. So I'm not going to go too much into this because we won't really use it in the rest of the class. The killing tensor has a form like this for Kerr. Where these L and M are basically two null vectors, which I'm not going to bother writing down. So any questions so far? Okay, so these are black holes. We should talk about their horizons. So if we take a look again at this metric in Borel-Linkous coordinates, we can sort of notice two places where this metric breaks down. The first is when sigma equals 0. And the other one is where delta equals 0. And you can see that both those quantities appear in the denominator for this metric. So it turns out that this sigma equals 0 is actually a physical singularity. We can calculate curvature invariants, such as the so-called Crutchman scalar, which we just get by contracting the Riemann tensor with itself. We could show this actually, and if we did that, we can show that actually blows up at sigma equals 0. And so this sigma equals 0 is actually equivalent to this quantity equaling 0. So we can see that unlike Schwarzschild, where we have the singularity just at r equals 0, 1 point, here we actually get a ring. However, before, if we're start at some large radius and move inwards, before we actually reach this point where sigma equals 0, we'll first have delta equals 0. And it turns out this is actually the horizon of the black hole. So, in particularly nice coordinates like we've chosen here, where we're axisymmetric, we're stationary, and where it just turns out that the horizon of the black hole actually occurs at a value of constant radius. There's a simple way we can use to determine where the horizon of the black hole is. And that's just to look at the surfaces of constant r and then figure out where they become null. So a surface of constant r being null is just equivalent to the magnitude of the unit normal, or of the normal to these surfaces of constant r equaling 0. This is just the unit. This is just a normal vector to constant r. And this, of course, if we just plug this in, this just gives us GRR equals 0. And if we look at what G with upper R indices is, it's just delta over sigma. So that tells us that when delta equals 0, then we have a horizon. So there are actually two values of R where delta equals 0. You can see it's just going to be a quadratic in R, so it's going to have two solutions. So we can call these two solutions R plus and R minus. And just using the quadratic equation, they're given by this. And so these actually, of course, so you can see that one value, R plus, is going to be greater than R minus. So we'll call that the outer horizon, and then R minus is the so-called inner horizon. Yeah, so just review what we did here. If we start at large R, these surfaces of constant R are space-like. And then as we move inwards, once we reach R plus, then these surfaces of constant R become null. And then for R in between R plus and I minus, it'll be time-like. So that means that R equals R plus actually defines a so-called event horizon that divides basically the causal path of future null infinity. So we'll write down or draw the conformal diagram for Kerr to show exactly what we mean by that in a second. But I just also want to note that, this metric not being well behaved at delta equals 0 is actually just an artifact of the coordinates we chose here. Probably in the same way as you're familiar with the Schwarzschild coordinates failing at the horizon of a Schwarzschild black hole. And we can choose better coordinates that are so-called horizon penetrating, and then there won't be any problems with the metric at the horizon. but it might not be as easy to do some of the calculations we're going to do and other metrics like that. For example, the Kerr shield metric.
Well,
Yeah.
sorry. Should there be a minus in the definition of sigma so that we can actually make that equal to 0? Because that's all positive, right?
Yes. Did I?
It's up there. Ah, okay, yeah.
Yeah.
Okay, yeah. All right, yeah, thank you.
Yeah, so I think that's right. Yeah, okay. Yeah, so it's just like this ring that we talked about here for that you get even in just flat space coordinates. Yeah. Okay. Yeah, one thing to note though is that if we have a greater than m, then basically we don't have any solutions to this quadratic equation, and so there isn't a horizon to our space-time. However, we're still going to get this blow-up singularity, so we actually have what's called a naked singularity, where the curvature is blowing up, but there's not a horizon to hide it from observers that are far away. So it doesn't seem that you can actually produce such objects in general relativity. And in fact, there's a conjecture that goes by the name of cosmic censorship that basically says that GR resists producing these singularities that would basically spoil what observers at infinity would see. So let's draw the conformal diagram for Kerr black hole. So here we have past null infinity, spatial infinity, and then future null infinity. So this is all the light rays coming in from infinity, and then all at the infinite past, and then all the light rays that are escaping to infinity and the infinite future. And then we have our horizon at R plus here that basically divides this part of the space-time here from the causal past of future null infinity. And then inside here, we have R minus. If you travel through R minus, then you could eventually reach this singularity at R equals 0. And then if you're at the particular values of this ring, you get this singularity. And like Schwarzschild, we can actually extend this solution. We could have a copy of the space-time over here, and then we can have a copy of this over here, and then put more copies, and so on. However, there's really no reason to think that's a physical picture at all. And so, we know that the Kerr solution is going to be a very good approximation to an astrophysical black hole, basically outside the event horizon, but we don't have much reason to think it's a good approximation inside. And so in particular, for a space-time that you actually form by collapsing some object down to a form of black hole, we think basically this picture should break down somewhere between r plus and r minus. So for the purposes of this class, we'll mainly stick to this region out here. Okay, any questions? Yeah, so next, so we talked about the horizon of the black hole. Let's talk about the so-called ergosphere. So if we look at the magnitude of our time-like killing vector, you can notice that this is just equal to GTT, which is equal to a squared sine squared theta over sigma at the horizon. And in particular, this quantity is greater than or equal to 0. And so what that means is that the time-like killing vector is actually space-like at the horizon, except where theta equals 0 or pi. And so we know the time-like killing vector is, of course, time-like at infinity. And so we can ask, as we move inwards in radius, what is the point it actually becomes null? And then, because we know that it has become actually space-like by the time it reaches the horizon. So null, of course, just means that magnitude is 0. And it's equivalent to delta being equal to a squared sine squared theta. Or if we use the definition of delta, we get basically the shape for the boundary between where the time-like vector or where the time killing vector is time-like and where it becomes space-like. So this actually defines what we mean by the black hole ergosphere. So if we draw what it looks like, have our black hole, and it's spinning. We're looking at the board of the plane is the one that contains the angular momentum vector. Then our ergosphere looks something like this. It meets the black hole at theta equals 0 and pi, and then in the equator, it extends to 2m. So you notice that when we let A go to 0 and just get a Schwarzschild black hole, the ergosphere moves to touch the horizon of the black hole and basically disappears. And if we look at a sort of top-down view, the black hole is spinning now this way. And here's our ergosphere in the equator again. So we'll talk sort of in detail and later in this week about how it's actually this ergosphere that allows you to tap into the rotational energy of the black hole. And that's where it got its name, because the word ergo refers to work. So you can use the black hole to do work in the ergosphere. But it turns out the ergosphere is also the region where time-like observers must rotate with the black hole. So to see that, So let's say we have some time-like observer with for velocity UA. And because it's time-like, we should be able to, its norm should equal -1. And then if we expand this out for our Borel-Lindquist metric, we get this. Okay, so what we want to note is that all these terms collected actually have to be greater than 0. So we can note that GTT is usually negative, but we just described how it becomes, it flips signs and becomes positive in the ergosphere. And then, of course, these terms are all positive. And so that means that it has to be this mixed term here that becomes negative in order to equal -1. And since G with an upper time and phi indices is less than 0, and ut is just the derivative of time with respect to proper time, and so it should be 0. It should be positive. We're left with the conclusion that u phi, which is just the derivative of the phi coordinate for this observer with respect to proper time, has to be positive. So in particular, it's not allowed to be 0. It has to be changing with time for an observer that's in the ergosphere. So let's consider observer with the following forward velocity. So here, alpha is just some normalization constant. We could get it just from this requirement that that chi contracted with itself is -1. And we just discussed over here that we can't set this omega term to 0. So let's instead choose an observer that has 0 angular momentum, where this basically the contraction of this observer with our axial killing vector is 0. So this is called a 0 angular momentum observer, or ZAMO. So if we expand this out, we just get this condition, and divide out by the alpha. So that means that omega, which is just the derivative of phi for observer with respect to a coordinate time now, is equal to this combination of the metric components. So this is basically the coordinate orbital frequency of these ZAMOs. And we can see that as we approach the horizon of the black hole, this quantity actually goes to the following. The dimensionless spin divided by 2 times the radius of the horizon. So we can actually interpret this quantity, we'll call it omega h, as the horizon frequency of the black hole. And in the last minute, we can note that if we define a vector where I've just replaced omega by now omega h, so this is a new Killing vector because it's just a linear combination of our previous Killing vectors with this omega h. And in fact, it turns out this is the Killing vector that has the event horizon as Killing horizon, which just means that this becomes 0 on the horizon. So this is basically the generator of the horizon for our Kerr black hole. And just finally, we can look at the values that omega h takes in a couple of limits. So in the low spin limit, where a bar is much less than 1, r plus is very close to its Schwarzschild value of 2m. And omega h is approximately just a bar divided by 4m. And in the extremal limit, where a bar is almost 1 minus epsilon, where epsilon is very small, then r plus is close to just being m, and the horizon frequency is given by this to leading nowhere in epsilon. Okay, so I think we're out of time here. So any questions? Okay, so if not, tomorrow we'll begin talking about geodesics on the Kerr spacetime.